Good afternoon. Thank you all for being here. I'd like to start by inviting you to think, what does 1 minute mean in your jobs? For us data scientists, 1 minute is usually the time to load some data. For most of us here, it's the time to get some coffee. But for ambulance service providers, being 1 minute faster represents a 24% increase in the odds of survival of heart failure patients. And one such provider to which every minute matters is our partner, the German Red Cross. They are part of the largest humanitarian network in the world, and they provide ambulance service here in the state of Rhineland Palatinate, where they have 400 ambulances and serve 700,000 emergencies per year, aiming to keep the response time of the emergencies under 15 minutes. But how do they manage this? Inside the organization, they have the figure of the dispatcher, a paramedic with special training, such as Simon. When you call the emergency number, Simon takes the call, identifies the type and the location of the emergency, and see which are the closest ambulance available. Now, if the emergency is highly critical, such as a heart attack, Simon will surely send the closest ambulance available. But let's imagine another situation. Let's say there is only one ambulance available in the city, and some others in a city nearby. And let's say I fall and break my leg. Now, if Simon sends the only ambulance available, the city will be left uncovered by some 20, 30 minutes, in which time, if someone has a heart attack, he will have to wait for an ambulance from city B to move to city A. Instead, Simon can make me wait 10 minutes more, which is okay because my emergency is not urgent. It doesn't represent a high risk for me. And I wait for an ambulance from city B in a way that city A keeps covered for the next 20, 30 minutes. Also, Simon can identify that there is an imbalance in the ambulance before the emergency happens, and then move an ambulance from city B to city A, or even temporarily deploy the ambulance to a position that's not an ambulance station, but has some infrastructure, such as bathroom and food for the driver. Today, all those decisions are taken based on his best judgment and experience, but with low machine assistance. This brings us to the problem we worked on this summer. We want to empower the dispatcher with machine assistance to know where to expect a higher number of calls, what we call demand forecasting, and how to place an ambulance to better serve those calls, which we call preventive relocation. All this leading to a more efficient usage of the resources and ultimately to faster arrival times. To do this, we use the data from the last 5 years of calls from the region of Ludwigshafen. And the first thing we can learn from the data is to predict the demand, where usually happens with more calls, based on the population and its age, and how this pattern changes over time, that's time of the day of the week, and also with the temperature and whether it's raining. So with this, we can tell which are the regions with more expected calls. Second, we can use the data of past calls to better estimate the time it takes for an ambulance to go to the emergency. So here you see the street network of the region of Ludwigshafen. And the color indicates where it's faster to reach and where it's slower for the ambulance of this region, with some distortion in the border zones because they are also served by ambulances of other regions. Currently, the system in place only uses speed limits to calculate these travel times. But with the data of the past calls, we can enrich this information with whether it's raining, whether the siren is on, and what is the time of the day and day of the week, and thus improve the travel time estimation. Our model improved the estimation in 1 minute and 14 seconds. It's a 35% improvement. And in 40% of the cases, this is more than the difference between the two closest ambulances. What means that this gain in the precision can lead to a better ambulance choice. Now that we know where we expect demand and how to better calculate travel times, we could identify a set of positions that are close to demand, that are not currently covered by stations and are nearby amenities as the most adequate for the temporary deployment. But some questions remain. Which ambulance should be sent? When should the movement be done? And where to a station or to these flexible positions? To help the dispatcher answer these questions, we built a system that gives a recommendation for the dispatcher. To do that, we first have a set of rules that looks to the current placement of ambulances and generate the set of possible relocations that are based on movements that make sense. By make sense, I mean that we don't want to move all the ambulances around. We want to move maybe one or two. We also don't want to send them too far away, but also we don't want to send them too close. So we have these movements that make sense given the current placement. Second, we give a score to each possible placement. For this, we look how well this placement supplies ambulances for the demand that we predicted across the region. And based on this heat map, we give an overall score to the placement. For example, putting all the ambulances in one city and leaving the other unattended has a bad score. While distributing the ambulances according to the predicted demand, we'll have a good score. Finally, we recommend the movement that makes sense and maximize the score. In this example, it's moving that ambulance from more central position, thus serving more demand. And this way, the system it can register the alternatives and its score in a way that the decision is auditable and explainable. We have a justification of why this movement was made. It's not a black box that just tell what to do. Finally, to evaluate this system, we create a simulation that runs through the calls that actually happen with and without the relocation in place to compare the response times. And we also try different frequencies of relocation, durations, that is, how much time should the ambulance spend in the new place, and slightly different ways to give the score. With this, the simulation indicates that incorporating our recommendations reduces up to 30% the number of calls that have to wait more than 15 minutes. And for these calls, it can reduce up to 5 minutes in waiting time. So the impacts of our project are that the better travel time estimation allows a better ambulance choice. The positions for temporary deployment brings the resources closer to more people, and the relocation recommendations reduce cases that have to wait more than 15 minutes, ultimately improving the speed of emergency operations through data-driven and explainable decisions, reducing every possible minute between assistance and those who need it. My name is Alex, and this summer I worked with Samia, Claudio, Vicente, and Diego under the mentorship of Julia, Gernot, Andrea, and Sebastian. We are excited to show you a prototype application and answer to your questions after